Hi, and welcome to this presentation. My name is David Andreas Borvik, and together with Chehu, we will present the project and the paper titled Monitoring in-home emergency situation and preserve privacy using multimodal sensing and deep learning. And now I'm going to talk a little bit about the dataset that we have been working on. The original dataset has 1.6 million images in total. That seems like a lot of data, but after cleaning it and pre-processing it, we ended up having 19,777 observations, with each observation including RGB image, depth image, presence data, which is the radar data, and the heart rate data. We had to resample the dataset since many images were quite similar from one second to another. This is due to the fact that most of the time people don't move that much around, at least if you're considering few seconds of time intervals, especially concerning older people. So the normal class, or null class if you want to call it, were quite dominant, so we had to take action on that part. We resized the images down to 200 by 200 to cope with the computational limitations, and we also normalized the images to be between 0 and 1 in floating value. The dataset has even more images than heart rate measurements, so we also had to align the timestamps of each heart rate with the correct image. And the images, the data is also specific to a certain person, so we had to align it with the correct persons. We had 20 people in our dataset. So after resampling, class labels were matched for each image according to a person's action, which were resting, lying on the floor, or moving. We considered the abnormal situation to be within the class lying, and we make the label, abnormal label, based on a threshold of 90 beats per minute, heart rate of 90 beats per minute within the class lying. We actually ended up excluding the thermal images since they were not that good at anonymizing the person. It wasn't good enough, at least we considered. So surely the RGB image is rather good enough at anonymizing, but we needed to keep the RGB images to have a benchmark for all models and configurations to beat. We also ended up excluding the respiration data since the respiration data had bad quality and it was not sufficiently matched in time with the other data that we had. We did a lot of pre-processing in this project, and we had to analyze the presence data further to coming from the radar to make use of it. And each observation has 1,466 features of numerical data, and we figured that it corresponds to the distance of between 0 and 10 meters. So we found a way to understand the data better by aggregating the values across all observations for each feature. So this is what's shown in this plot here. This gave us insight into the most significant features in terms of distance between the person and the radar sensor. For the dataset that we've been working on, it's clear that the people mostly stayed within 0 to 1.36 meters of distance away from the sensor. So we decided to focus more on the 200 first features of that data, and we created wavelet images and recurrence plot images based on the first 200 features. And actually, the use of 200 features fitted well for the dimension chosen for the images, because we ended up having 200 by 200 images dimensions for both the images depth and the RGB images, but also for the wavelet and recurrence plot images. As briefly mentioned in the previous slide, we constructed images from the presence data, and we focused on wavelet representation and the recurrence plots representation of the first 200 features of the presence data. So we ended up having 2 extra sets of images, having the dimension of 200 by 200. It's the images that you can see animated in this current slide. So for the wavelet images on the left side, the y-axis represents the distance of a person from the sensor, and the x-axis represents the absolute value of the wavelet transformation coefficient of the signal. And for the recurrence plot is created by producing a square matrix where its elements corresponds to the number of times a state or a feature or the value reoccurs. This method embedded the distance of a person relative to the radar sensor into a 2-dimensional image grid. So we animated this over some seconds to show the person movement of a person detected by the presence radar, so which you can see in the animation GIF. So by doing this, it enabled us also to construct data fusion of the numerical data together with the 2-dimensional images that we worked with. For all our setups, we performed the experiments both for 2 classes classification and 3 classes classification. And setup 1 is the univariate data model that we made. You can see the architecture in the table. For the CNN, it's a sequential CNN model. And the neurons is actually just a variable which reflects the hyperparameter for the grid search that we present in the paper, and 2 or 3 outputs based on if it's a 2 classes classification or 3 classes classification. And for the presence data, the LSTM, using the numerical values, is actually, we use the sequence to vector LSTM model, sequential model. Moving on to the next setup, setup 2, where we utilize the data level centrifugation method, where we take in 2 different images from the 2 different sources and merge them together. Yeah, we used Adam optimizers for all our experiments, and both for the 2 and 3 classes classification. This setup also is for both those cases, and we had then CNN with depth images and recurrence plot representation for one configuration, and another configuration CNN with depth images and the wavelet transformation representation of the presence data. And you can see that the size of the image is different from the previous. That's because of the fusion of those 2 images. It creates a new image with different size. In setup 3, we performed a feature level fusion experiment. So the architecture actually fused together the features from two different CNN models. So you can see the architecture in the table. The first model takes in the depth images, and the second takes in either the wavelet or the recurrence plot images, and then creates features, and those features are merged together or concatenated. And lastly, they are fed through dense layers and the last output layer. In the last setup 4, the decision level fusion method, we actually perform the classification separately between, or we have two types of classifiers. One is the CNN images directly, and they are performed actually the classification and outputs the result, the classified result. And further downstream, we apply those classifications to or feed it through either the support vector machine classifier or the random forest classifier as the second classifier. That's what separates decision from feature level fusion, is that on the feature level fusion we concatenated the features, but here we actually do the classification all the way for the CNN, and then further downstream do a second classification using a different type of classifier. Here's our results from the 2 and 3 classes classification. The accuracy of the decision level fusion methods came quite close to the performance of only using RGB images, with a performance of 99.73% accuracy. And for the 3 classes classification, all the fusion methods, and even only just using the depth images, had high accuracy. The data level fusion and the decision level fusion outperformed the reference model. And the model having the highest accuracy is the decision level fusion combined with depth and recurrence plots. In most cases, we find the support vector machine performs better than random forests. In this work, we used RGB depth images and presence data together with heart rate data from smartwatches. We wanted to classify normal and abnormal situations for an in-home emergency situation system. And we wanted to preserve the privacy of the people in the data. So we mainly focused on depth images and different types of sensor fusion methods using presence data and the smartwatch heart rate measurements. We found that the decision level fusion outperforms the other approaches in classifying normal and abnormal situations by 99.98% accuracy. This is even better than using just the RGB images directly. So this work gave us an additional methods or approach to supervise health status of older people and at the same time protect their identities.